Hello everyone. Today we learn about stationary values of many, or in this case especially two variable functions. So, we already discussed the stationary points of a function of one variable. That is, if df equal to 0, it means we have a stationary point that is either a maxima or a minima. So we had a minima if d squared f dx squared, the double derivative of the function, is greater than 0, and a maxima if it's less than 0, and if it's equal to 0, there's no information. So since we started studying partial derivatives, or the derivatives of more than one variable functions, so how would the minima and maxima of a function be in this case, that is a function of more than one variable? What would be the minima and maxima? Let's say an example. Say we have a cup, that is a cup like this. This is the handle. Excuse my bad drawing. This is a cup. This is a two variable function, and this would be the minima, or the bottom of the cup would be the minima of this cup, right? Since the cup is a two variable function, that is a function of x and y, the minima would be the bottom of the cup. Also, if you place the cup upside down, that is like this, this would be the maximum. In this case, if it's placed upside down, the top would be this point and this would be the maxima. So this would be how the maxima and minima of a two variable function. This would be the physical, this would be the graphical representation. So there's another kind of point. So we have seen the maxima, the minima of a two variable function, how they would look like, and we have another point called the saddle point. What is that? All of you have heard of horses, right? So the back, or the place where we sit in the horse, can serve as a good example. It goes like this, goes like this, and like this. This is the back of a horse. We usually sit here when we're riding a horse. So this, look at this. This thing looks like a minima. This place looks like a minima, right? Because it's like this, curved like this. This should be a minima along this line, right? But along this place, this is the highest point, right? If we go like this of a horse, this place is the highest point. This place is the highest point. So along the x, if we consider this an x-axis, this is a minima along this, the x region, and along the y region, this is the maxima. So what is a saddle point? A saddle point is a maxima in one coordinate and a minima in another coordinate, or vice versa. We call it a saddle point. So now we have introduced the minima, maxima, and saddle point of a function of two variables. Now let me get rid of this. Okay, so now let's write about the stationary point of a two variable function. So for a function of two variable, it should be clear that a necessary condition for stationary point, which is either a maxima, minima, or a saddle point in this case, is finding this should be a partial derivative equal to 0. Both of them is a requirement. Both of them is a requirement that if both of them are 0, then we have a stationary point of a two variable function. It's quite similar to the one variable case, in which we had only one variable and we differentiated that, and if it's 0, we have a stationary point. So now, why is it a necessary condition? Because if you see, derivative is like a slope, right? So if the slope is a horizontal line, what is the slope of a horizontal line? It's 0. Same. You can understand graphically that this should be the case. Since derivatives are like slopes, if we draw the slope at this point, it's 0 because it's a horizontal line. Same there, same here. Okay. Now, by analogy with the single variable, for single variables we had minima if the second derivative is greater than 0, a maxima if it's less than 0. So in analogy with that, we can do the secondary two variable case as well. What would that be? So by analogy with the single variable case, we see that and should be positive if we want a minima, and if we want a maxima, it should be negative. That is min and max. It's simple. It's similar to a single variable case, but we only have two criteria. That is, it should be 0 for both. It should be greater than 0 or less than 0 for both the variables. So let's write it out. Let's write everything out. This is called the second partial derivative test. The second partial derivative test. This says the first is minima. We have a minima of the function of two variables if the second derivative is positive and del y is less than times del y squared. Again, we would have a maxima if it's the same, but with maxima if and is negative, right? And this case would still be there. The partial with respect to x and partial with respect to y should be less than, and now the saddle point case. The saddle point would hold saddle point. So let's write it at the top. So the saddle point condition, so let's write it at the top. Saddle point. So if it's a saddle point, if let's say, let's write here, the double derivative with respect to x and with respect to y have opposite signs. That is, one is negative, one is positive, and vice versa. Or xy, which is, I'm sorry about that, which is greater than So what do we have here? So we have a minima if the second derivative of both variables is positive, maxima if the second derivative of both variables is negative, and this condition is satisfied, and this condition is satisfied for these two. And we have a saddle point. A point here is a saddle point. A stationary point is a saddle point if the second derivatives with respect to one variable and another variable have opposite signs, or this condition is satisfied. This is the second partial derivative test for a two variable function. So let's sum up here. First, we learned how a maxima or a minima for a two variable function may look like, which is we learned with a cup example. Then we learned about the saddle point, that is a maxima with respect to one variable, but a minima with respect to another variable, which is a saddle point basically. Then we learned about the stationary point, necessary condition for a stationary point. Then we went on and learned about the second partial derivative test, which says minima if this, maxima if this, and saddle point if this. Thank you.